This video, we are talking about one of the biggest changes to gasoline combustion engines of the 21st century, the widespread adoption of direct injection. In the year 2000, very few cars were relying on this technology, instead opting for port injection, and yet now it's extremely common. But there were very real challenges into implementing direct injection, so in this video we're going to be focusing on 3 of those problems. So visually the change seems very simple. Instead of injecting our fuel into our intake ports, now we are injecting that fuel directly into the cylinders. However, the effects from this change are fairly dramatic. So for our port injected, we have large droplets injected at a low pressure. This gives the fuel a lot of time to mix, because not only does it have the time to mix within the intake ports, but also the entire intake stroke as well as the compression stroke. Whereas your direct injection, you may still be injecting fuel during that compression stroke, so it has much less time for that fuel to mix. So you have lots of time for the fuel to mix with the air, which gives you a great air-fuel mixture when using port injection. This is great for cold starts, and it's also good for emissions to make sure all that fuel and air is well mixed. Now for direct injection engines, we have small fuel droplets that are injected at a very high pressure. And the neat thing about this is you have an in-cylinder cooling effect. So as that fuel vaporizes within that cylinder, it cools that air down and cools your cylinder temperatures. So you have less likelihood for knock, you can run higher compression ratios, you can run higher boost, and you can run at higher efficiencies. And so as a result of all of this, the industry changed and they went towards downsized gasoline direct injection turbocharged engines. So instead of a V8, perhaps now a vehicle is running a twin turbocharged V6, and where a vehicle was previously running a V6, it's now probably running a turbocharged inline 4-cylinder. Now there are some problems associated in making this dramatic change. I wanted to focus on 3 very serious issues that aren't quite as commonly discussed: chain wear, fuel dilution, and low speed pre-ignition. So let's start off with timing chain wear, and chain wear is ultimately the result of soot formation within the engine. So soot are the tiny particles that are the result of incomplete combustion of a fuel droplet. So looking at our engine here, you have that fuel combusting from that direct injection. You have, of course, rich air fuel pockets within this direct injection system because you don't have quite as much time for all of that air and fuel to perfectly mix. And so those rich pockets, you can have incomplete combustion occur, which can form this soot, as well as combustion products that then hit cylinder wall. So if you have that fuel that's partially burned and then it ends up hitting that cylinder wall, it could stop that combustion process and then it could form soot. Then you have blow-by and your piston rings bringing this soot down into your crankcase. And so that soot then accumulates in your oil. Now you might think, well, can't you just filter this out? You don't actually want to filter out the soot. You could end up clogging up your oil filter and then run into larger problems. So instead you use dispersants in the oil so that that soot doesn't agglomerate, form into larger molecules of soot. And so by doing so, you're just trying to keep that soot floating within the oil so that eventually when you do change your oil, you just remove all that soot. Now, the thing is, for most engine parts, it's not a problem for that tiny little soot particle to be floating around. You have plenty of clearance between these engine parts with your oil film. However, there are certain spots like timing chains, and specifically silent timing chains, where you have these really tiny clearances with your pins. So you've got these timing chains which are made up of pins and links, and so within these tiny little pins here, you can have that soot get in there, and that soot can cause abrasion within that and start to wear away. And so if you have hundreds of these little spots where you have tiny amounts of wear, then across that entire chain, you can start to have chain elongation. So the chain isn't stretching, you're not stretching out metal, instead you're just having elongation from wearing away at these little pins. So that means now your valve timing is going to be off, so that is problematic. Your intake and your exhaust valves are not going to be opening at the correct time. So how do we prevent chain elongation and thus the altering of our valve timing? Well, you test for it. So there's a test called the Sequence 10 engine test, which is an ASTM standardized test. In this test, you run an engine for many hours, and for the majority of the test, the engine is injecting excess fuel, thus running rich and creating a lot of soot. The piston ring gap is also increased so that you have excess blow-by, thus putting a lot of soot into the oil. and you measure the timing chain length after engine break-in and then after the test is completed, and the chain can't have elongation greater than a small fraction of a percentage. So how do you know if the oil you're using passed this test? Well, you have to look at the back of the bottle for the certifications. Anything with API SP or ILSAC GF6 will have passed this test. Another challenge is fuel dilution of your oil. So for example, let's say we are starting up our vehicle cold. Of course, it's going to start running with a rich air-fuel mixture, especially with direct injection, because it knows not all of that fuel is going to be able to mix with the air. So it's going to inject a bit more to help you start up that engine. So you're injecting in extra fuel, and also, because it's direct injection, some of that fuel is just going to be sprayed directly onto those cylinder walls. And so it might just hit those cylinder walls and end up working its way down into your crankcase. So that unburnt fuel and that extra fuel that you're injecting, especially when this engine is cold, it's going to hit those cylinder walls, and then your pistons and blow-by are going to cause that to get washed down into your crankcase. So then that fuel mixes with your oil, and it dilutes that oil, and it reduces its viscosity. So if you take that viscosity out of the ideal range for that specific engine, remember, the manufacturer is choosing a very specific viscosity for their engine, and now you're taking it and you're decreasing that viscosity. So you could have increased engine wear as a result of decreasing that viscosity. So if you go on a bunch of short trips again and again and again, and you're never letting your engine get up to operating temperature, well, you're just going to start to accumulate more and more. If you do this only once, it's not a big deal, right? Eventually, when you go on that long trip, the oil heats up enough that you vaporize that fuel from the oil, and then it ends up getting burned off through the PCV system. But if you just do repeated short trip after repeated short trip after repeated short trip, you start to accumulate that fuel within the oil, and it doesn't take a whole lot of fuel to get into that oil to really start to drop that viscosity rating. So it's important, and this is more of a driver solution, that if you do regular short trips, you really need to incorporate a regular long trip in there where your engine oil actually gets up to operating temperature, so you make sure to burn off any fuel that may be diluting that oil. Finally, we get to low speed pre-ignition. So what is this? Well, during our compression stroke, we're compressing our air and fuel, and before our spark plug fires, we have pre-ignition occur from a hotspot somewhere within that cylinder. So that hotspot causes the air and fuel to start burning before our spark plug has actually fired. Then that flame front starts to propagate out from whatever hotspot ignited it, and this starts to increase the surrounding pressure of the entire cylinder. So as you increase that cylinder pressure, and again, we're compressing that air and fuel down, so we're getting really high pressures within our cylinder, and then we have auto ignition or knock occur in other pockets where that air and fuel just starts to combust. So your timing is happening too early, and you're not controlling when your ignition timing occurs. So this can cause severe engine damage. Now, why does this occur? Well, it's been noted to occur when you have really high cylinder pressures at low RPM. And what engines are commonly having this? Well, small, downsized, gasoline direct injection, turbocharged engines running high boost. You've got those really high cylinder pressures, and we're asking for more and more torque available at low RPMs, and so that's giving you that condition. Now, one of the things that has been found to be a cause of this is a detergent formulation in engine oils. So one solution is changing the oil formulation in order to prevent LSPI. Okay, so how do we ensure an oil doesn't cause excessive LSPI? Well, again, there's an industry standard test, the Sequence 9 engine test. Here we have an engine operate at a low speed with a high load where LSPI occurs, and we run the engine through 4 repeated tests which add up to hundreds of thousands of ignition cycles per cylinder. For each of these 4 tests, the number of pre-ignition events is measured, and there is a maximum that cannot be exceeded in order to pass. So, how do you know if the oil you're using passed this test? Again, look for the certification. Anything with API SP or ILSAC GF6 will have passed. So, using an oil with the latest certification is a good idea in general, but this is especially true if you're using a modern direct injection turbocharged engine.